Alright, so in this video we're going to formally introduce limits of sequences, and so we'll start here with the definition. And so it says that if a sub n can be made arbitrarily close to a number L by taking n sufficiently large, we say that the limit of the sequence a sub n exists, and we write this using limit notation as follows. It says the limit as n approaches infinity of a sub n is equal to L. And sometimes we'll also use this notation. This says a sub n approaches the number L as n approaches infinity. Okay, so now when the limit of a sequence exists and it equals the number L, okay, we say that that sequence converges to the number L. Okay, now the intuitive idea behind convergence, as you can see in the figure here, is that the terms of a sub n cluster around this number L as n approaches infinity. Okay, so to be a bit more precise, this means that if you give me any window around L, okay, that's what you see here in blue, then you can find an index such that all of the terms of the sequence past that index will fall within that window. Okay, and that's true of any sized window. So if I have to be within, say, a millionth of L, then I can find an index. I might have to move way out to the right, but eventually I can find an index such that all of the terms past that index will be within a millionth of this number L. And that would be true of a billionth, right? I might have to go further out in the sequence, but again, eventually all the terms past some index will be within, say, a billionth, right? So that is the sense in which I say the terms cluster around this number L. Okay, so now here is another example on Desmos. We're looking at the sequence n squared plus the cosine of pi n all divided by n squared. And you can see the terms here in green, and here's the corresponding function as we've discussed. Okay, so what you can see here from the visual is that the terms kind of dance around this line y equals 1, and the gap between our terms and y equals 1 is decreasing, right? And this has a limiting value of 1. Now what I was saying there just a moment ago with this idea of this window, okay, so if I give you a window and I know that the limit of the sequence is 1, then you can go ahead and find an index such that all of the terms past that index will fall within that window. So you might miss a few terms at the front end, like here my threshold is 0.037. Okay, and notice the first, second, third, fourth, and kind of borderline there with the fifth term, they all fall out of that window. But then everything past this term, they all fall within. Now, of course, the smaller the threshold, like if I go out to, say, 0.01, right, then I could miss a bunch of terms out the front end. But again, eventually, okay, I'm going to find an index such that all of the terms past that index will fall within that window. Okay, so this sequence has a limit of 1. All right, now do all sequences have limits? No, and if the terms of a sequence don't approach a single number as n increases, then the sequence has no limit, and we say in that case the sequence diverges. All right, so now let's look at some examples. And so for the first example, we're looking at the sequence 1 over n, so 1, 1/2, 1/3, so on and so forth. Here's a graph of that sequence. So as we let n get larger, of course, these terms get smaller and smaller and approach 0, right, as we let n approach infinity. So we can express that using limit notation. The limit as n approaches infinity of 1 over n is equal to 0. All right, now for the second example, n over n plus 1, we've seen this a couple times. It's 1/2, 2/3, 3/4, 4/5, so on and so forth. Here's its graph. Okay, and as we've already alluded to in a previous example, this sequence has a limit of 1. Okay, so to see that algebraically, first note that if I divide the numerator and denominator by n, okay, I can rewrite this n over n plus 1 expression as 1 over 1 plus 1 over n. Okay, so now as n gets infinitely large, this term, 1 over n, as we just noted up here, approaches 0. So that says that our sequence, n over n plus 1, will approach 1 over 1 plus 0, which is just equal to 1, of course, as n approaches infinity. Okay, so we can write this using limit notation as follows. The limit as n approaches infinity of n over n plus 1 is equal to 1. All right, third example, we've got -1 raised to the n plus first power. So first couple terms are 1, -1, 1, -1, so on and so forth. So here's a graph, right? We're just bouncing between these two values, 1 and -1. Okay, so here the terms don't approach any particular single value. Okay, so we're just taking on these two different values, 1 and -1 here, but we're not clustering up around any particular single value. Okay, and so for this reason, okay, this sequence diverges. Okay, so another way to say that, as we mentioned before, okay, the limit here does not exist. We just say this does not exist. Okay, so this is a divergent sequence. We're not approaching a single value there. The fourth example is a little bit more subtle. It's 1, 0, 1, 0, 0, 1, 0, 0, 0, so on and so forth. Okay, so the string of zeros is increasing in length as we move from string to string. Okay, so a very common answer here is that this sequence converges to 0, and the thinking there is that, well, the string of zeros is becoming arbitrarily long as we move further and further out in the sequence. And while that is true, the problem there is that you're always going to have a 1 down the line. Okay, so if I think about putting a little window around y equals 0, the problem there again is that is there an index that will capture all the terms such that all the terms will be within that window past that index? And the answer there would be no, because if I set my window to be within, say, like a millionth, well, there's going to be a 1 down the line, and it's going to jump out of that window. Okay, so you're going to have a long string of zeros that all fall within the window. That's great, but you're always going to jump back out. Okay, so this sequence also diverges. Okay, we're not approaching any one particular value. Okay, cool. So in the next video, we're just going to look at a whole bunch of examples, and I'll highlight some various algebraic maneuvers and remind you of some things about limits that you likely would have seen in Calc 1 and Calc 2. So I will see you there. Thanks so much.